Okay, for this lecture, I'm going to introduce the concept of free fall, and then I'm going to do an example of that and an example of horizontal motion. So, when dealing with vertical motion, we use y as our position variable instead of x. So these are the same kinematics equations we learned already. I've just replaced x with y to indicate that this motion is vertical. So again, same equation, just put y instead of x. Or sorry, same equations with four of them. So free fall motion is where an object is just experiencing acceleration due to gravity. And that acceleration points down through the entire motion. So we have a particle diagram with our particle and vector diagram. So if we start off and launch some object from the ground with an initial velocity, this is what it looks like. And the whole time through this motion of it going up and when it comes back down, it's experiencing acceleration due to gravity that is pointing down the entire time. And so what we see is we launch it up with an initial velocity, and then over time that velocity gets smaller and smaller because the acceleration points the opposite direction, it's slowing it down until finally we get to the peak of the motion, the highest that the object is able to go. Because at that point, its velocity is now 0 because acceleration has been pointing the opposite direction and decreasing it the whole time. And so this is the point where it also goes from going up to going back down. And so this is the same like it's not taking a U-shaped path. We're assuming it's going up and straight down, but it's trying to show you the velocity vectors for the downward motion. But we can see it does the opposite thing because it's now moving down and the acceleration is pointing down. Those are in the same direction. It's going to cause the object to speed up. So when we go from the ground and throw up, our velocity gets smaller until it reaches 0. And then when it turns around and heads back down, it gets larger until it reaches the maximum value. We can also see the value of the free fall acceleration in a velocity versus time graph, the whole of free fall motion. The slope is going to be negative the entire time, and the value is actually negative 9.8 meters per second squared. And that is what we use as the free fall acceleration due to gravity. And we represent that by a little g, which you will see on the next slide. We also have it as negative for a couple of reasons. First off, because it's always pointing down, and for us, down is negative. In the slope of the velocity graph, it is a negative slope, so it also follows along that. So those are the reasons. So we can now put this value for the acceleration into our equations from before. We dropped off that first equation because remember that's for constant velocity as in no acceleration. And we know we have acceleration in this case. So like I said, it's represented by little g. And all we did here is instead of the a sub y that was in these spots, we just put negative g instead. So negative g times the time interval, negative 1/2 g times the time interval squared, and negative 2g times the displacement. So these are the equations you want to use for vertical motion and, well, free fall motion specifically. And again, it is the same equations we use for horizontal motion. We just change the variable, and then also because this is free fall, we replace the acceleration. So now we're going to do an example of this, and then a complicated horizontal motion example. Here is, I'll read you the problem real quick. What happens if a person on a cliff throws the rock straight down instead of straight up? To explore this question, calculate the velocity of the rock when it is 5.10 meters below the starting point and has been thrown downward with an initial speed of 13 meters per second. Yeah, let's work on this example. Okay, and so the first thing we want to do is just draw the situation. It's a really simple drawing, but I think it will help us. Um, so we have a person on some sort of cliff, and they are throwing a ball down with some initial velocity. Or actually, we know the initial velocity, but the initial. And what we want to know is what the velocity is when it gets, once it's traveled 5.1 meters. So one thing we can do is label our initial position, this one, y initial, just like at the top of the cliff. And we'll say that is 0 meters. And then we're looking for when it gets this y final, which we will give it a negative 5.10 meters. And this is just because we set the origin above this, going below. The signs will work out in the end. And oftentimes we're not doing a problem where the object starts high up and comes down, lots of times from the ground enough. So you won't always need to set the cliff height as 0 position, but we're going to do that this time. So now let's write our knowns and unknowns. So, and some of them I wrote over there, but we'll write them again. Y initial is 0 meters. Y final is negative 5.10 meters. Its initial velocity is 13 meters per second. And then there's one that's not in the question prompt, but we know what it is because we know we're doing free fall. And that is that the acceleration is negative g, which is negative 9.8 meters per second squared. Okay. Then unknowns. We don't know the final velocity, which is what they asked for. We also don't know the time interval. They don't ask us for that, so we might not need it, but we should write it down anyway, just in case. Okay, cool. So now let's look at the kinematics equations. I'm going to leave out the one where it requires 0 acceleration because we know we're not dealing with that situation. So v final equals v initial plus, maybe we'll write, no, I'll just write it with a and we will plug g in later. You don't have to do it this way. You can use g in your equation already, but y final equals y initial plus v initial times the time interval plus 1/2 acceleration times the time interval squared, and v final squared equals v initial squared plus 2 times acceleration times the displacement. Okay, now we look at our equations to see what we know and what we don't. First equation. We want that final velocity. We don't know. We know the initial, we know our acceleration, we don't know the time interval. That's two unknowns. We probably can't use that equation, or at least not on its own. We definitely can't. We know our initial and final position. We know our initial velocity. We don't know the time interval. We know acceleration. We don't know the time interval. So this equation, it only has one thing we don't know, but it's not the thing we're looking for. So let's see if the last one will work for us. Okay, so we want that velocity. We know the initial acceleration and displacement. Cool. Let's use this equation. That way we don't have to solve for time first. And before we write out the equation, let's just also define what the displacement is. That's y final minus y initial. So that's negative 5.10 meters minus 0 meters. So that's just going to be negative 5.10 meters. Just so we have that complete before we move on. Let's pick a different color, I think. Guess blue. Okay, let's see. V final squared equals V initial squared plus 2a times the displacement in y. And we know what V initial is, like I said. Oh, although I just realized I forgot something. V initial is also down. So our initial velocity is negative. We gotta remember that. Although it's squared in this equation, so it's not gonna change things. Let's see. I think, yeah, the only thing we need to do is just square root both sides to actually solve for V final. So that'll give us V final equals the square root of V initial squared plus 2 acceleration times the displacement. And then square root And I'm just going to plug in my numbers. So this is negative 13 meters per second, whole thing squared, plus 2 times negative 9.8 meters per second squared, and then negative 5.10 meters. So, we have a square root. You can't have a negative square root, or, I mean, you can if you want imaginary numbers, but we do not. But it's okay, because our negative signs are going to cancel out. These ones will cancel, and then that one cancels when it's squared. So we don't have to worry about that part. So this is, I forgot. 1 second. I might have to just calculate it again. Let's just calculate it. 13 square root of 13 squared plus 2 times 5.1. And this is 16.4. That would be meters per second. And we just have one additional thing we have to remember here is that this is down. Down, so it needs to be negative. This equation, when we use the squared equation, it's not going to give us the sign because it's just like how square root works. So in this case, you have to remember that, okay, it's down, so it's going to be negative. But yeah, so that's that example. And we did the same procedure we do for horizontal motion. We drew a diagram, wrote our knowns and unknowns, figured out what equation to use, rearranged it, and solved. And then we took a moment to make sure that we were keeping track of the direction of our final velocity. Okay, now we're going to do a horizontal motion example. And this one I already have the car drawn so that I didn't have to draw it 3 times. Okay, so let me read you the problem. A car is traveling. Sorry, before I read it, I just remembered this is the challenge problem from Thursday's in class assignment. It's a complicated one, so I wanted to not just give you the solutions, but show you how to work it out. Now I'll read it. A car is traveling at a speed of 30 meters per second, a typical highway speed on wet pavement. The driver sees an obstacle ahead and decides to stop. From this instant, it takes him 0.75 seconds to begin applying the brakes. Once the brakes are applied, the car experiences an acceleration of negative 6 meters per second squared. How far does the car travel from the instant the driver notices the obstacle until it stops? Okay, so we have the car at these 3 different instances. So we have it initially, we have it once the driver like that processes and actually puts their foot on the brake, and then once it stops. And I'm going to label each of these times. So I'm going to label them with the position in it. So this will be X0, this will be X1, and this will be X2. And we know the velocity initial or velocity not, if I'm using that, 30 meters per second. We also know to go from position 0 to position 1 that there's no acceleration happening in that time because that's the time the person needs to process that they need to turn on the brakes. So that velocity is still 30 meters per second. And then finally, they're going to come to a stop. So this final velocity is 0. Okay. And I think I will leave it as that for now, and we'll do our knowns and unknowns and come back to our diagram. Maybe. I might change my mind. We'll see. Okay, so let's do those velocities that we know. The initial and velocity at position 1, those are both 30 meters per second. Final velocity, which we're calling velocity 2, is 0 meters per second. Acceleration is negative 6 meters per second. Oh, squared. I was putting the squared first. Let's see. And then we have time interval 1 is what I will call the time interval. Let's do some color coordinating. So for here, we have time interval 1, and also we will say displacement 1. Let's see. I think that's actually all of our knowns. We'll see. Unknowns, we don't know. Time interval 2, time interval 2. And this is also displacement 2. Okay. So we don't know time interval 2. We don't know displacement 2. We also don't know displacement 1. And there's one other thing we don't know, which is the total displacement, which is what we're asked for. Because we're asked from the moment that they see the obstacle ahead, to when they're actually stopped. So that includes that 3/4 of a second of processing time the person needs to actually put on the brake. So that's going to be displacement 1 plus displacement 2. And I didn't write that as displacement. Displacement 2. Okay. And yeah, we have those areas labeled. I think we are good for now. Oh, I guess I can add that the total displacement is this. Delta X total, not 2. Okay, let's look at our equations now. So let's see, V initial plus, no, I don't know what I'm making it up. V final equals V initial. V final equals V initial plus A delta T. We're in X now. X final equals X initial plus V initial delta T plus 1/2 A delta T squared, and V final squared equals V initial squared plus 2A times the displacement. So we're going to just start with displacement, like the initial displacement 1. So what color was that? Purple. So we will go through the equation for that specifically. So we know, with this one, actually, forgot we do need the other equation, because for that time period, we have constant velocity. X final equals X initial plus velocity times the time interval. So, these equations all have acceleration, and our acceleration is 0. So we could use the long kinematics equation, but it actually just turns into this equation. So we want the final position, we know initial. We didn't set it to 0, we should do that, but it's okay. And we know these. So we can use this equation to find displacement 1. And let's start that. So I'm actually just going to turn it into displacement, so we don't even have to worry about setting the initial position. So we'll just subtract the initial position on both sides, and that gives us X final minus X initial, which is the displacement, V delta T. Okay, so that's what we're going to use, but we should write out what variables are what, because again, we've changed our labels a little bit. So let's do that. So X final in this case is X1. X initial is X naught. Displacement is displacement 1. Time interval is time interval 1. And this velocity is velocity initial, which is also velocity 1 because it doesn't change in that time. Okay. Now, going back to the equation, we have displacement 1 equals velocity initial times the time interval 1. And so let's calculate that. 30 meters per second times 0.75 seconds. This gives us 22.5 meters. So that's how far the car travels before the person even actually is able to apply the brakes, just because of reaction time. Okay, next one. Now we want to know what displacement 2 is. So now let's go through. We can't use this equation this time because we have acceleration now. We know what final and initial velocity are. We know what the acceleration is. We don't know the time interval. We don't know the final position. That's what we would like to know. We know what the initial is there, because we just found what our displacement was before that. We know the initial velocity, don't know the time interval. No acceleration, don't know the time interval. Okay, this one has two unknowns. I don't think we can use that one. Let's see. We know the velocities and acceleration, and we want the displacement. Okay, this is the equation we want to use. We don't need to use this equation. I mean, we can because we only have one unknown, but we're not asked for the time, so why do extra work? Okay, so let's see. V final squared equals V initial squared plus 2a delta x. Let's define the variables in this situation. V final is velocity 2. V initial is velocity 1. And the displacement here is displacement 2. Cool. Now we can solve for the displacement. V final. Oh, no, let's write these with our labels we just gave. V2 squared equals V1 squared plus 2a delta x2. Okay, and then we'll subtract the initial velocity on both sides. Losing track of what colors I'm using. V2 squared minus V1 squared equals 2a delta x2. And then we'll just divide everything by 2 times the acceleration. And that will get us solving for that displacement. V2 squared minus V1 squared over 2 times acceleration equals displacement 2. Okay, let's plug this in. So velocity 2 is 0. Minus 30 meters per second is the initial velocity. Oh, each of these is squared. And then 2 times negative 6 meters per second squared. So this gives us a displacement of 75 meters. So that's displacement 2. So get the final answer, we just combine the two displacements so that we can get the total displacement to go from seeing the obstacle to a complete stop. And so that's 22.5 meters plus 75 meters, which is 97.5 meters. So that's pretty far to travel to stop. But yeah, that is the answer to this question. And this is, like I said, a little bit more complicated because, again, you have to break our situation up into two chunks because we have different relevant variables in these two chunks of time. Like the very first one, we know how much time passes. There is no acceleration. We need the distance. And then for the next one, we don't know how much time passes, but we know what the acceleration is. And we want the distance again. So that's all for this. Hopefully this didn't end up too long. I tend to go long when I'm doing examples. Have a good day.